Confused about composite functions, and at times finding its domain can also be confusing. So come join and watch this video at Cikgu Zana's channel.
Assalamualaikum, I'm Cikgu Zana. Welcome to my channel, and I'm all about helping the pre-U students of Mathematics M score A's in their exam. So if you're looking to use my video, please do subscribe and click the bell to be notified when I release a new video. So let's watch my video.
The content of today's video is definition of a composite function, finding the composite function and its domain, existence of a composite function, and lastly, finding the restricted domain of a composite function. Firstly, let me introduce the meaning of the composition of two functions. Consider the given two functions g and f. Together, these two functions can be combined to create a function f of g, where the output of the first function g becomes the input of the second function f. This action defines a composite function. Let's take a look at what this means. If I'm a taxi function g, I pick up values from the green area, multiply them by 2 and drop them off in the blue area. For example, the value of 3 is picked up, multiply 3 by 2, and the value of the product 6 is dropped off in the blue area. Then, another taxi function f will pick up the values from the blue area, add 1 to each, and drop them off in the yellow area. Hence, the output value of 6 is picked up by taxi function f, add 1 to 6, and the value of 7 is dropped off in the yellow area. This forms a composite function f of g. Now, let us understand the composition of functions using Venn diagram. Consider the Venn diagram showing the three sets A, B, and C. The first function g maps the element x in A into gx in B. The second function f would then operate on gx, mapping it onto C, thus forming fgx. Therefore, the composition of the two functions g followed by f is denoted as f of g and is called as the composite of f with g, which produces fgx. Thus, the composite function f of g is described as the function that maps each element in set A to the elements in set C. The function notation of f of g is such that x maps to fgx for all x in domain G. Finding the domain of a composite function. If f of g exists, then domain fg is the same as domain G. When finding the domain, be careful of function in rational form, as you must never divide by 0, and root function, as you must never take a square root of a negative value. The first example is to find the composite function f of g and state its domain. F of gx means the output of the function g, which is square root 1 minus x squared, becomes the input of the function f. Hence, the value of x in f takes the value of square root 1 minus x squared. And when simplifying, we have 3 minus x squared. Thus, the composite function f of g is 3 minus x squared. Now, since f of g exists, the domain of f of g is the same as domain g. Thus, the domain of f of g is for all x in the interval from -1 to 1 inclusive. Example 2. Finding the composite function g of f and state its domain. The composite function g f x means the output of function f, which is x squared minus 2, becomes the input of function g. Hence, the value of x in g takes the value x squared minus 2, and thus the composite function g of f is 2 over x squared minus 1. So what is the domain of gf? Since g of f exists, the domain of gf is the same as domain f, which is for all x greater equal square root 2. Now, observe that the composite function gf is a rational function. So when finding the domain of gf, we must make sure that the bottom part of the fraction is not 0. And it is proven here that for all values of x greater equal square root 2, the values of x squared minus 1 is always greater equal 1. So the statement the domain gf equals domain f still holds. So how do we determine whether two functions can be combined to form a composite function? To determine whether f of g exists, the range of g must be a subset equal set to domain f. To determine the composite function g of f exists, the range of f must be a subset equal set to domain g. Example 3 involves the concept of existence of a composite function. To determine the domain of f of x is not defined when x is 0. This is clearly illustrated by sketching the graph of f of x. From the graph of f of x, domain of f is, and the range of f is. For the function gx, the value under the square root must always be greater equal 0. From the graph of gx, the domain of g is, and the range of g is. And if you have forgotten how to find the domain and range from the graphs, please click the link given in the description below. To explain why f of g exists, we need to analyze the values of range of g and the values of domain f. We can illustrate the values of the range of g and domain f on a number line. The first line represents the values of range of g, and the second line represents the values of domain f. Notice that the line range of g is part of the line domain f. Thus, range of g is a subset equal set to domain f. Thus, the composite function f of g exists. Now we can compose the composite function f of g. Here, the output of the function g, which is square root x minus 1, becomes the input of the function f. Hence, the value of x in f takes the value square root x minus 1. Thus, the composite f of g is 1 over square root x minus 1. Now, is domain f of g equivalent to domain g? Observe closely. F of g is a rational function. Since it is a rational function, the bottom part of the fraction cannot be 0. Thus, for f of g to be defined, the values of x must be greater than 1. Hence, the domain of fg must be in the interval from 1 to infinity, where 1 is not inclusive. Example 4 is another example on the existence of composite functions. First, let's determine the range of the two functions for the given domain. This can be done by sketching the graphs of the two functions. From the graph of f of x in the domain from negative infinity to infinity, the range of f is from negative infinity to 0 inclusive. And from the graph of gx in the domain from 0 to infinity, the range of g is from negative infinity to infinity. Hence, to determine whether f of g exists, we need to analyze the values of the range of g and the values of domain f. Observe that the values of range of g is the same as domain f. In other words, the range of g is equivalent to domain f. So, f of g exists. For part B, to determine whether g of f exists, we need to analyze the range of f and domain g. By displaying the values of range of f and domain g on a number line, observe that the line domain g will never intersect the line range of f, clearly indicating that the range of f is not a subset of domain g. Thus, g of f does not exist. For composite functions which do not exist, it is still possible to construct a composite function by restricting the domain of the first function. Here is an example where f of g does not exist, but we need to determine the domain of g so that f of g exists. The domain and range of f and g can be determined by sketching the graphs of the two functions. From the graph of f of x, domain f is, and range of f is. From the graph of gx, the domain g is, and the range of g is. To explain why f of g does not exist, analyze the values of the range of g and the values of domain f. Displaying the values on the numbered line, observe the range of g is not a subset of domain f. Thus, f of g does not exist. For f of g to exist, the domain of g needs to be restricted so that the range of g consists only of numbers in the interval of the intersection of range of g with domain f. This can be done by letting the range of g, negative x squared plus 10, to be greater equal 1, which is the same range of values as domain f. Simplifying, we have a quadratic inequality. Solving the quadratic inequality using the number line method, the range of values that satisfy the quadratic inequality is from -3 to 3 inclusive. Thus, the restricted domain G is in the interval from -3 to 3 inclusive. This is what happens when the domain of G is restricted. Sketching the graph of G using the restricted domain, the range of G is in the interval from 1 to 10 inclusive. Analyzing the values of the new range of G and domain F, and displaying the range of values of range of G and domain F on a numbered line, observe that the range of G is part of domain F. Thus, range of G is a subset to domain F. Thus, f of G exists. Hence, you can now find the composite function f of G. The output of Gx, which is -x squared plus 10, becomes the input of the function f. Simplifying, we have square root 9 minus x squared. Therefore, the composite function f of G is square root 9 minus x squared in the interval of x from -3 to 3. Similarly, in example 6, we need to determine the domain of f such that G of f exists. Analyzing the values of the range of f and domain G, the domain of f is restricted by letting the range of f 2x minus 6 to be greater equal to, which is the same range of values as domain G. Solving, we have x greater equal 4. Hence, the restricted domain of f is for all x greater equal 4. Using the restricted domain of f, the graph of f is sketched. From the graph, the range of f is in the interval from 2 to infinity, where 2 is included. Now, from the domain of G, it is observed that the range of f and domain G have the same values. So we can conclude that the range of f is an equal set to domain G. So, G of f exists. Now you can find the composite function G of f. Here the output of f is the input of G. So G of f is square root 2x minus 8 for all x greater equal 4. Conclusion of today's lesson. If f and g are functions, then the composition of f and g is defined by where the output of the inside function g, gx, is the input of the second function f. Below is the algorithm for the existence and finding the domain of the composite function f of g. First, determine the range of g and domain f in interval form. Is the range of G a subset equal set to domain F? If yes, then f of G exists, and domain f of G is the same as domain G. But be careful of rational and root functions. Never divide fractions by 0, and never take the square root of a negative value. If no, then f of G does not exist. But by restricting the domain G, f of G exists and the domain of f of G is the same as the restricted domain G.
Okay, that's about all. Hope the video was helpful. If you are new here, please subscribe to my channel for more video lessons. If you have any questions, go ahead and ask in the comment below. I'll see you then in my next video.